All right. Good day, everyone. My name is Will. This is Michael, and we are here all the way from Melbourne, Australia, representing Monash HPR Rocketry, and we're very excited to present to you today a significant reduction in the computational cost of our CFD processes. Cool. So just a quick presentation outline. We'll first begin with CFD and its current limitations for us, reduced order modeling, what it is, and our solution, Andromeda, and then capabilities in simulation design, finally finishing with future work. Great, so just a brief overview of what Monash HPR Rocketry does in terms of trajectory simulation. We have an in-house developed 6-degree of freedom trajectory simulator called SASN, and this requires extensive CFD to get high-fidelity trajectory simulations. As you can see in the figure, SASN in the dark blue has significantly outperformed open source software since its inception. And this is mainly because of the drag database that it's produced. Great, so what is our CFD process and its current limitations? For some context, SASN runs a variety of parameters and provides simulation data for each of these parameters. These are called Monte Carlos, and we can identify how sensitive a rocket performance is to key parameters in the vehicle, which is extremely important for understanding risk. Currently, though, we have no practical means of studying the effect of body design, as a change in body design means that you have to create a whole new CFD drag database. Cool. So why is good CFD so important? Well, quite simply, a rocket is extremely sensitive to drag. A 1% error in drag corresponds to a 1% error in apogee, roughly, for our rocket Valkyrie. In the past, we've found that small design changes have had large impacts on performance, and therefore, in the design cycle of Valkyrie, it's extremely important to understand how body changes change the performance and safety of the rocket. Cool. So while good CFD is still extremely important, in the design cycle, we have a limited amount of time, so we must find a way to produce these CFD databases quicker. Bit of context in how we produce our CFD databases. We first do an open rocket simulation of our rocket, and we generate a discrete set of points at a mark, angle of attack, and pitch. And these amount to about 110 states that we have to simulate in ANSYS Fluent. Often a single simulation in Fluent takes 300 iterations to converge, and roughly 45 to 90 minutes to solve on our supercomputer. And obviously, 110 of these states amounts to days and weeks of computational time. So this makes rigorous design review sweeps, time-consuming, and Monte Carlo analysis of our body design infeasible. Great, so we have a problem here. Generating drag databases through CFD is extremely time-consuming, and it limits body design to things we already know, and it restricts innovation, basically. So we need a means of determining drag much faster at an acceptable rate for early prototyping. So what's the solution then? Well, the flow of a rocket at a given angle of attack, let's say 1 degree, for a constant Mach number and a roll, should be relatively similar to that at 2 degrees at the same state. Therefore, it would be ideal if only a few cases had to be simulated in our drag database on Fluent, and we could use the other points to potentially predict the flow of these withheld data points.
Yeah, great. So this is where our solution, Andromeda, comes in. So accurate numerically derived reduced order model for efficient data analysis, or Andromeda for short, is our custom in-house developed tool written in Python for developing reduced order models, which predict CFD flows, just like a conventional solver would. But unlike conventional solvers, which take hours or more to solve a single state, Andromeda can do so in minutes. And so it follows many of the lessons we learned whilst developing our trajectory simulator Saturn. Namely, we've made it highly human readable, lightweight and scalable, and we've emphasized ease of access to data for simplifying investigations and debugging. So how does it actually work? Well, what we do is we take a small amount of points in our aerodynamic database as training data, and we put the answers Fluent to solve normally, and then using this smaller set of training data, we pass it into Andromeda. Andromeda then looks at these CFD flows and deconstructs the data, and it tries to find underlying correlations between these flows and creates a meta model. And then using this meta model, we can then reconstruct the remaining fluid flows in only a few minutes, which are then passed back into ANSYS Fluent, which just derives the drag from the flow solutions, and we get our full database. So how can we actually deconstruct the data? Well, every flow state contains several key parameters, such as your flow velocity components, your pressure, temperature, and so on. And these parameters all have a unique value at every cell in the mesh. So it makes sense to represent every parameter as its own state vector, where every component in that vector is the value of that parameter at a given cell in the mesh. Right. So then it follows from our previous observation that two similar flows will also have a similar flow, will also have similar state vectors. So as you can see in this toy problem here, we've got a state vector representing a flow at 1 degree pitch, angle of attack, 2 degree angle of attack, and 3 degrees. And visually, you can see in this very simplified case that the 2 degree angle of attack flow is approximately equal to half the 1 degree case plus half the 2 degree case. So what's the bottom line here? Well, this demonstrates that we can represent flows as approximately equal to linear combinations of other flows, which is very, very powerful. However, oftentimes it's a lot more practical to work with a vector basis that spans your space rather than just dealing with your training vectors directly. And so we obtain our basis by taking all the parameter vectors for a given parameter from every single training case, and then inserting it into one giant data matrix XP. And then we conduct something called the singular value decomposition on that matrix, which gives us three smaller matrices, U, P, sigma P, and V transpose P. And we're especially interested in U and sigma. U gives us the basis that we're looking for, and then sigma describes how much each of these basis vectors, how much of the variance each of these basis vectors contain, basically. And so as we mentioned before, we can now use these basis vectors to reconstruct entirely new flows, just by using matrix multiplication. And so, as you can see visually here, what these basis vectors visually represent, they're almost like Fourier modes to your flow, right? So you can see at the top, you have a flow, and then after conducting the SVD, you can break it up into these basis vectors, and these basis vectors, they're like the resonant frequencies of the flow. And then if you take a new linear combination, that is to say, you multiply these basis vectors by different coefficients, you can construct an entirely new flow. That's reasonably similar to the original one. And so following on with this analogy, that means that these A coefficients, they're like the amplitudes to your Fourier, Fourier. So it's essentially like taking a Fourier series. And so this process is industry standard, and it's used a lot in statistics and dynamical systems. Right, but the problem now is, how do we know these amplitudes? Well, we do know what amplitudes are in the training data. We just want to figure them out for the remaining data. And if we tactfully place our training data so that they bound all of our remaining cases, that means that we're essentially just interpolating coefficients. So this is now just a simple interpolation problem. So we investigated a variety of different interpolators to address this, and they can be broken down into statistically and physics-informed methods. Statistically informed interpolators are conventional in that they just look at patterns in the data and just try to regress it. Whereas physics-informed methods are a little bit more involved. They leverage things like the Navier-Stokes equations to try and provide a more sound estimate based on the knowledge of the physics. So after this investigation, we found that quadratic spline provided superior regression capability for the least amount of overhead, which is in line with Andromeda's design requirements of being lightweight and easy to read. And so the way we do this is, in our database, we hold our mark constant, and then we just interpolate along these mark contours. Now this has two advantages. First of all, holding your mark constant now just gives you one-dimensional data, and since it's one-dimensional, spline works. And secondly, by holding your mark constant, you're fundamentally interpolating over a more structured data set, because at a constant mark, your data is going to regress in a much more behaved way. And we can exploit that to a remarkable degree of accuracy here. As we can see, despite the Navier-Stokes being incredibly chaotic, nonlinear, and difficult to solve, just through splines, we can construct entirely new flow states with, as you can see, incredible precision, with something as simple as this, which is what Andromeda is capable of.
Awesome. So that's Andromeda in theory, but how does it actually perform in practice? So for Valkyrie, we found Andromeda actually performs remarkably well. If we look to the figures here, we can see Andromeda in the orange line. That's Andromeda's prediction. And the blue line is Fluent's solution, converging over a set number of iterations. And to remind you that these Fluent iterations take over an hour to solve, whereas Andromeda can produce this in just 2 to 5 minutes each. This is incredible because instead of spending weeks and months fumbling over these CFD processes, we can just get it done within days. Cool. So why is Andromeda so good? Well, if we look here, we can see an x component of velocity plot of the cells around Valkyrie's fluid domain. If we look at the percentage error in the second figure down, we can see that Andromeda predicts the flow remarkably well, with only a few regions showing any difference to the converged solution from Fluent. If we take a closer look at the fins of the rocket, we can clearly see this is a pitch of 5 degrees and a mark of 0.2. There's a clear asymmetry in the solution, which is what is expected. And behind the tail of the rocket and after the rail guide, there's a clear slowing down of the x component of velocity, which is to be expected. Comparing this to ANSYS Fluent's initialization in the solving process, which takes 2 minutes, we can see that Andromeda provides a superior guess. Great, so what are the time savings we have here? Well, a typical CFD simulation takes 45 to 90 minutes, whereas Andromeda takes 2 to 5, with just a 15-minute overhead to produce the model. This is practically negligible compared to the time required for a Fluent simulation, and as such, we are only constrained to the amount of training data we choose to provide. For Valkyrie, we decided to take 30% of the total database as training data, and that theoretically means we can run 3.3 times as many sweeps compared to a normal database generation. At a minimum, we like to take 3 to 6 geometries along a linear change, and so in the time we can produce a full investigation for a parameter query, would have taken time to produce 1 CFD database normally. So this is just incredible. So what this allows for us is we can now do Monte Carlo analysis on body parameters. The rigorous analysis of external geometry was not possible until now, and this gives us unprecedented insight into Valkyrie's performance and was absolutely essential in the initial stages of Valkyrie's design.
Great. So now I'd just like to quickly touch on the future of where we want to take Andromeda. Right. So whilst Andromeda performs remarkably well in 80% of cases, where we get within 3% drag error, in the remaining 20%, sometimes these outliers form in the mode regression, where they're beyond the general trend of the data, and this means that our interpolators don't quite pick them up very well. This is during the early prototyping stages of Valkyrie's design when we use Andromeda. This is not a significant concern because we're not too concerned about getting pinpoint trajectory predictions. We just want to understand the general behavior of flight so we can optimize our design. However, obviously, it would be nice to mitigate this and make and account for these outliers, as well as pushing down this 3% error as far as we can, so that it will be possible to leverage Andromeda's remarkable speed at any stage of the design cycle, including at the very end when we are concerned about pinpoint trajectories and we need very, very precise drag. And so how can we do this? Well, if we take Andromeda's predictions and provide them into Fluent as an initialization, this means that the 80% of cases, which are already quite good, we'll just solve immediately because they're practically already a converged solution. And then the remaining 20% of cases will just get cleaned up by Fluent. So we've already done some preliminary investigation into this, as you can see in these histograms. So what you're looking at is on the x-axis, you have the percent difference between the prediction and the true value at a given cell. And on the y-axis, it's the amount of cells that have that error. So if you look at the histogram on the left, that's one of those 80% of cases. As you can see, Andromeda in blue far outperforms Fluent's default initialization method, which gives us confidence that indeed we could solve this very quickly and give us within 1% drag error, which is what ANSYS does. ANSYS Fluent does. And then even more impressively, on the right, what you're looking at is the error formed by the prediction of the interpolator or by Andromeda on this outlier here. So even that outlier that's so far away from our interpolator, Andromeda still actually predicts 30% better on average than Fluent's default initialization, which means that even outliers that we don't capture quite so well will still actually solve faster using Andromeda than if we just did it by Fluent directly without Andromeda. So to summarize, extensive CFD is paramount for accurate simulations. especially considering how sensitive we are to drag, and even small changes in design will have a massive impact on performance. So we want to fully understand this, and hence we need extensive CFD for this. However, doing this is very expensive and requires weeks to months of simulation time, which is just practically not acceptable. But that being said, the symmetries across an aerodynamic database can be exploited to massively increase speed and enable otherwise impossible body design analysis. Thank you, and we're happy to take questions. Oh,
speed or design. So you're in the limit to
sorry, so you're asking where the limits are, or
design. Where do you start speeding?
yeah, so this is based on SVD, and so SVD is very symmetry dependent. So if I go back to here, so it's very symmetry dependent. So basically that means the second that you start to get misalignment, then this breaks down. And so this is not at all an issue for us though, because we're constantly interpolating. So this and machine learning in general is very, very, very good with interpolation, but performs quite poorly in extrapolation. So as long as we interpolate by bounding our points, we maintain the global symmetry of the data set, and hence within that 80% confidence bound, we get within 3%.
Okay, the data influent question already as well.
When one thing that you have problem in machine learning, especially when you're using a curve fitting thing, whether it's slimes or quadratic polynomial curve fitting, is a problem over fitting.
Yes, that's right. Yes.
So you got about 30% for training and test. But what about the validation? How did you validate? Did you have a separate subset of data you used to validate?
Fluent only gives us validation.
Make sure that you weren't being overfitting kind of behavior.
Yeah, exactly. That's a very good point. So in regards to this, first of all, so we validate this from Fluent, as we can see, where are we? Here. So we see our withheld cases. So the orange cases are not seen by Andromeda, only the blue cases. And we see that with that 30% training data, we fit really quite well. And furthermore, I should clarify that this is trained in every sweeper we run. So this is not like a global model that we use. What we do is we take training data and then we use that training data to fit that particular model. And then as the sweep proceeds, we progressively add more and more points into the interpolation. So every now and then you will get some points like that outlier we saw that's captured slightly, that's captured not as well as some other points, but it doesn't matter because the overall speed is significantly faster. So even if you do get a few cases which are not optimal, it doesn't matter in the overall scheme of things. Yeah.
Okay, now good one. And so most of the initial data was initial training data. Did I do that correctly?
Yeah, so basically OpenRocket is just to gather a template for our drag database. So we have, obviously Rocket spends time at a mark number, angle of attack, and roll, and we just want to find roughly what this is. We get that from OpenRocket, and we get that from OpenRocket.
Yeah.
And then we take those points, we solve for them, and then we can run a simulation in our inbuilt simulator, which then predicts the trajectory much better, and we can really refine these points. Yeah.
So it's just compared the analysis. How about
With what? Sorry. With flight data. So this is less about flight data because we've had plenty of validation with our simulator Saturn. So we can compare that to flight data many, many times, and that's proven to work successfully. So what we can do is we can generate this CFD database, and we can find points in this database, and we can validate that against flight data. And then when we use Andromeda, we then can validate that against the flight data and expect the results. Exactly right. Yes. Yep.
Click on it.
Thank you everyone for coming. Cheers.